So thank you, Masayoshi-san, for this introduction and description of the personal insight of how the Fukushima accident made you think about the development in the energy field and the technological foresight that brought Sonsan and SoftBank into the artificial intelligence development has also made Son and SoftBank realize the potential of renewable electricity that in a similar way will disrupt industries. One of the global leaders in describing how this disruption will occur is Tony Seba. And I will hand over the screen to him now to describe how this development has started in the world since 2011 and what he projects will happen in the near future. So Tony Seba, the floor is and the screen is yours.
Thank you. I'll restart. This is a disruption. Thank you again. This is New York City, Easter Parade in 1900. There is one horse, one car in a sea of horses in New York City, 1900, one car. There it is, one car. Only 13 years later, there is one horse in that picture. A 9,000-year-old transportation industry horse was disrupted in just 13 years. And that's how quickly disruptions can happen. And a disruption is when a new product or service creates a new market and also destroys an existing one. And it's usually the experts and the insiders and the mainstream analysts who don't understand disruption or who dismiss it. It's not going to happen. It's not going to happen now. That happens time and again, very smart people. And that's why over the last 15 years, I have worked on a technology disruption framework to help understand disruption, analyze, and also anticipate in advance, not in hindsight, but in advance. And let me walk you through some of the elements that I study in disruption. One of them is technology cost curves. And as we know, for instance, in information technology, there's computing, which improves at about 40% per year, data storage, digital imaging. There are many technologies that have advanced very quickly, and each one at its own pace, different cost and capability improvements. So in 2014, when I published a book called Clean Disruption, this is what I projected for the cost of lithium-ion batteries over the following up until 2030. And for instance, I said that by now, 2021, the cost of lithium-ion batteries would fall under $150 per kilowatt hour. And at the time, I was told that was crazy. It could not possibly happen. And yet, not only did it happen, it actually happened even more quickly than what I projected. But the point is that you start with the cost curve. But the big disruptions are enabled by convergence. And I'll tell you what that means. If you think of 2007, we got both the iPhone and the Android in the same year, 2007, not 2005 or 2009. The reason it was 2007 is that all the technologies that made a $600 smartphone possible converged 2007. So any of 30 companies could have actually built a $600 smartphone. Motorola could have done it. Nokia could have done it. but they didn't. The ones who did it were Apple and Google. And that's another lesson of disruption. Disruptions are enabled from the outside, not by incumbents, but by outsiders. Neither Apple nor Google had ever built a phone before. Another important point is the S-curve. So back to the car and the horse, the adoption of the car happened as an S-curve, never a line, it's an S-curve. But here's the most interesting thing, that car market share went up from 11% to 85%, 21% in just 10 years. So even more than 100 years ago, the bulk of the disruption happened in only 10 years. Not only that, it happened while we built two new industries, auto and oil. We built the new road infrastructure. We fought a war and the world's meanest pandemic in history. And despite all of that, most of that disruption took place in only 10 years. So anyone who tells you that a disruption in energy or transportation cannot happen in 10 years is not looking at reality. Because today, S-curves, adoptions, are happening even more quickly. So we would expect disruptions to happen even more quickly than in the past. But despite that reality of quick S-curves, we see conventional forecasts miss out every year. For 20 years, the IEA, International Energy Agency, every year they draw a straight line for adoption of solar, and every year they have been wrong by 30, 40, 50% every single year. But the reality is this, that it's starting to look like an S-curve adoption. And also, the collapse of the old industries happens as an inverted S-curve. And that's what, for instance, have been happening with coal. This is the reality. And every year, they project a straight line into the future. Not going to happen. It hasn't happened. And as I said before, really smart people and really smart companies believe these linear mistakes. GE, for instance, one of the premier industrial companies of the 20th century, lost about $200 billion in market valuation because they believed in the future of natural gas and nuclear and so on. GE almost went bankrupt because they believed a linear projection, which has never happened. So part of my work is to answer this question. Why do smart people at smart organizations consistently fail to anticipate or lead market disruptions? And the quick answer is this: the linear mindset. They treat life as a line. They can see only a straight, and also silos. Energy is here, transportation is here, food is there. They don't see the links between all of those connections. Another important thing in disruption is business model innovation. So Uber and Lyft, for instance, Uber, only 7 years after it got started, had more bookings than the whole taxi industry in America. 7 years. And 11 years after they got started, the car rental industry started to collapse. Again, disruptions can happen in 7, 10, 11 years. And this is really important. Major disruptions are basically phase changes to a new system. So the car was not a faster horse, which is what analysts would have told you in 1900, that the car was a faster horse. It was not. The car market was 100 times larger than the horse market, and of course cheaper. So it was both cheaper and a lot larger, right? So it was not just what I call a one-to-one substitute of the existing system. So let me summarize how disruptions happen. We have a long equilibrium, which means in transportation, for instance, we've had the same internal combustion engine automobile for 100 years. We've had the same grid for about 100 years. So that's a long equilibrium. And then suddenly we have a convergence of technologies, like 2007 with the iPhone. And as that convergence happens, it opens up a large possibility space, but not everybody sees that. Entrepreneurs do, and they enter the space and they create new products and services. They push, so think, 10 years ago, Tesla and so on. They push the cost down and the capabilities up. And after a while, the long equilibrium ruptures. And then the new rises. So we saw how last year, Tesla went from maybe $100 billion to $800 billion valuation. The new rises and the old collapses. And that happens also very quickly. And then the new becomes the new incumbent. And that's how disruptions have happened for hundreds of years. So let me walk you quickly through the disruption of transportation. Again, in 2014, in Clean Disruption, I predicted that the cost of a 300-kilometer electric vehicle would fall from about $80,000, which was back then, to today about $30,000 in just about 6 or 7 years. And again, like the battery projection, a lot of folks said that that was a crazy prediction. And yet, in fact, today we have cars that are a lot cheaper than that. And if you keep that cost curve going, you can see that every single new car is going to be electric by 2030 for purely economic reasons. Now, we're going to get a lot of other benefits, but for purely economic reasons, it's going to be electric. And what sounded crazy 6 or 7 years ago is what Volvo is going all electric by 2030. VW is going all electric by 2030. We are going to have hundreds of new EVs over the next few years. So now it's happening almost exactly as I predicted. And there's more to that because this is not a one-to-one substitution. An electric vehicle lasts anywhere from 800,000 kilometers to 1.6 million kilometers. So if you're a fleet like Amazon or Uber, over 10 years, you can drive the fleet 160 kilometers every year. For 10 years, you would need 1 electric vehicle or 7 gasoline or diesel vehicles. It's a no-brainer on a per mile basis for fleets to go electric because it already makes economic sense, which is why Amazon and other companies are already going all electric because it makes economic sense for them to do that. But the convergence of transportation is what's going to enable the big disruption. And I'll be very brief for that. It's on demand, autonomous and electric, owned by fleets, not individuals, because fleets drive 10 times more than individuals every year. So the day that autonomous technology is accepted, level 4, and the cost per mile of per kilometer of transportation is going to be 10 times cheaper than the cost of owning a car, any car, 10 times. And in my study of disruption throughout history says that 10x has always, always, always enabled a quick disruption. And I see that happening in the early 2020s, over the next year, 2 years. And the cost of one of these vehicles is going to be cheaper per mile than even owning a car, even maintaining a car on a going forward basis. And what we saw from Tesla is more or less the prediction that I had made 4 years ago. which is that the cost per mile is going to fall by about 5 times for them, and eventually maybe about 10 times. So if I'm right about these disruptions, 95% of passenger miles will be electric by 2030. That's only 10 years as an S-curve, right? S-curve for the electric and downward S-curve for the gasoline and diesel. Now, let me talk about my latest study about the disruption of energy. The question that I asked myself and our team asked was, is an electric power system consisting only of solar, wind, and batteries, that's it, possible by 2030? And if so, how much will it be? So before I go into that, let me show you the technology cost curves. By now, you know that solar is the cheapest source of energy on the planet, period. No subsidies, cheaper than coal, gas, nukes, anything else today, unsubsidized. Not only that, the cost of what's called nearly firm generation, which means solar plus maybe 4 hours of storage, or wind plus 4 hours of storage, is lower than the operating cost of coal, nuclear, oil, and gas already. What this means is that even if the power plant for nukes or coal are free, just the cost of operating those plants are more expensive than all the costs of solar plus 4 hours of storage. So even today, it makes no sense economically to have any new nuclear or coal or anything like that. But on top of that, the cheapest sources of energy are going to get about 70% cheaper over the next decade, 70%. So solar went down by 82%, and we expect another 72% drop in costs. Wind, which went down 46% over the last decade, we expect about the same over the next 10 years. Battery costs went down by about 87%, and we expect another 80% over the next 10 years. So again, back to the question, can we have a system composed only of solar, wind, and batteries? So we took real world demand and solar and wind generation data, hourly generation data, and we put it in a simulation, in a systems dynamic model, to see how it could scale, if it could scale to 100%. And we started first with California, Texas, New England, and then we did it for other regions. We did Germany, we did India. And here's the first finding. Yes, there are thousands of possible electric power systems that are just solar, wind, and battery. Hundreds, thousands. But here's what we found. There is a non-linear trade-off, what we call the clean energy U-curve, between generation and storage. So you can have a lot less storage, but to do that, you need a lot more generation. And you can have a lot more storage, but with a lot less generation. But it's not a linear relationship, it's non-linear. And that is, so essentially it means that it's not about taking out a nuclear power plant and putting in a solar power plant. It's not one-to-one. It's a whole new system that would be created. And so the least cost option, for instance, has 4 times the generating capacity of the existing electricity system, 4 times. But so we'll see how much it costs. And for that system, you would need anywhere, depending on the region, from 1 day to 5 days of storage, of battery storage. So one of the things that we found is if you need only 1 day to 5 days for any region, Germany, New England, Texas, India, you don't need seasonal storage. So the idea that you need weeks or months of storage between seasons is not right when you do this simulation of solar, wind, and battery. And also, what we found is if we start now and we finish by 2030, 100% solar, wind, and batteries is the cheapest possible electric power system, period. It's cheaper than even maintaining the existing system. And that is across the board true for all the regions that we saw. And again, I emphasize, this is not the same old system. Solar, wind, and batteries are not just cleaner form of conventional generation. It's a different system. And one of the most important findings is what we call superpower. And this means that this system is going to generate super abundant, zero marginal cost energy, super abundant. How so? Let me explain. So because we designed the system to meet every single hour of every single day of the year, essentially we're creating extra capacity. And that extra capacity that is not used for that 1 hour can generate power all the rest of the year. How much power? It can generate twice as much power, free, right? Because you've already covered the existing demand. It can generate up to twice the power on most days of the year. And that is superpower. That's free, superabundant energy. And that is not disruptive just to electric power. That is disruptive to all forms of energy. How so? Well, if you cover the existing demand, right, first, then superpower would generate so much extra power that it could cover, for instance, in California, all the miles, all the electric transportation kilometers when California goes 100% by, say, 2030. And on top of that, it can cover all residential heat if we go electric, if we electrify residential heat and commercial heat. So it's disruptive not just to electric power, but to everything. Same thing, Texas. It would cover pretty much everything, residential, transportation, and commercial. So it's disruptive to all that. And by the way, if Texas had 100% solar, wind, and battery, as described here, they would have had 49 hours of energy storage, 2 days of storage. So they would not have gone through that outage, through that horrible outage that they had to go through. And even if half of the existing generation had failed, essentially the existing generation would have generated so much more that it would have been okay, no outage. So this is a more robust system than the system that we have today. And in fact, it's also the cheapest system. In Texas, it would be 2.6 cents per kilowatt hour. And the economics are very disruptive too. And here is one of the most important things that I want you to get out of this talk, which is this. Once you have the 100% SWB system, if you invest an extra 20% in the system, you can get up to 200 to 300% more superpower. Repeat, 20% additional investment can get you 200 to 300% more superpower. This is more like information economics. This is no current source of energy can compete with this. This is information economics. So again, New England, which is at about the same latitude as Japan, an extra 20% investment would give 210% additional superpower. In Germany, which is north of Japan, an extra 20% investment would give them 373% more superpower. This is disruptive to everything. This is a whole new system, a whole new way of thinking about this. Cheap, superabundant energy always leads to prosperity. And when it's clean energy, it leads to even more prosperity. And this is really the only way for us to solve all the sustainable or most development goals by the United Nations. So I'll close this. We're on the cusp of the fastest, deepest, most consequential disruption of energy and transportation. It's going to happen over the next 10 years, maybe 15, and it's going to happen for purely economic reasons. And this is not just an energy transition pushed by the government. This is a technology disruption. Thank you. Thank you.
Oh, thank you, Tony, for this wonderful presentation. I'm very happy that your slides started working because the slides were worth every minute.
Thank you.
We're now going to turn the screen over to Amory Lovins, who already almost 50 years ago wrote a book where he described the potential of renewable electricity and renewable energy in combination with intelligent, engineered, energy efficient systems. And he will now mainly speak about energy efficiency potentials, and we can then discuss how they fit together, the renewable energy development and the efficiency. Amory, the screen is yours. You are muted. We can't hear you, Amory, because your microphone is off.
Okay, I think I'm back now. Sorry.
You are.
Okay. Ohio gozaimasu. I'm going to try to follow Tony's wonderful talk by saying how to make it even easier and cheaper, because I think he was being a bit conservative. Renewable energy can bring climate solutions even sooner and more profitably when combined with efficient energy use. So please, therefore, let me remind you about how to design whole systems for radical energy efficiency. This proven practice applies orthodox engineering principles, but asks different questions in a different order to get very different design answers. Around 1975, US government and industry all said that primary energy productivity, the GDP produced per unit of primary energy used, could never go up. A year later, I heretically suggested it could rise 257% in 50 years. So far, it's risen 154% in 44 years. But just the innovations already added by 2010 can raise energy productivity by another threefold, twice what I originally thought, at a third the real cost. And today that looks conservative, because optimizing buildings, vehicles, and factories as whole systems, not as piles of parts, can often make very big energy savings cost less than small or no savings, turning diminishing returns into increasing returns, just like Tony talked about. Economic geologists know that a mineral's economically extractable reserves are only a small part of the resource base, but can expand with innovation. Similarly, reserves of conventional energy efficiency, like the bright green zone in these mineral resource definitions, are several-fold smaller than the full efficiency resource. Yet, ore bodies are finite and depletable concentrations of atoms, while energy efficiency resources are infinitely expandable assemblages of ideas, depleting only stupidity, a very abundant resource. That's documented in this free paper with a fun 4-minute video abstract. Its evidence across all sectors shows that unlike oil or copper, most new energy efficiency reserves cost less than those we are now exploiting, because they come not from adding more or fancier devices, but from using fewer and simpler devices, more artfully chosen, combined, timed, and sequenced. So how do we do this magic? One of my early mentors, the inventor Edwin Land, said, "Don't undertake a project unless it is manifestly important and nearly impossible." He also said, "People who seem to have had a new idea have often just stopped having an old idea." Asian tradition similarly urges us to seek original mind, beginner's mind, child mind, opening ourselves to new ideas by shedding all assumptions and preconceptions. That's the first and hardest step in the method of integrative design. As the Zen Roshi Nanin told his visitor long ago, you must first empty your cup. So thus, with beginner's mind, never having built a house, hence not knowing what was impossible, in 1982, I did the conceptual and energy design of this owner-builder house where my wife and I live near Aspen at 2,200 meters above sea level. The outdoor temperatures used to go as low as minus 44 Celsius, with up to 39 days of continuous midwinter cloud. But our house does no combustion. That's so 20th century. Super insulation, ventilation, heat recovery, super windows that insulate like 16 or 22 sheets of glass, would look like 2 and cost less than 3, made it 99% passive solar heated, 1% active solar. Efficiency added less construction cost than eliminating the heating system subtracted, saving also 90% of electricity, 99% of water heating energy, half the water, all paid back in 10 months. The central atrium, seen here in a February snowstorm, has produced 77 passive solar banana crops. Without needing to look like this, our house helped inspire several 100,000 European passive buildings with no heating and roughly normal construction cost, and a house in Bangkok providing better comfort with similar cost and 90% less air conditioning energy. Nearly everyone on Earth lives in climates between Bangkok's and mine. An integrative design gives many benefits from each expenditure. The white arch behind me or at the top of the upper middle photo has 12 different functions, but it has only one cost. So we start at the end with the effect we want. To deliver that effect, we optimize buildings as whole systems, not as a pile of parts. We pay for the efficiency by shrinking the needed supply. We maximize those capital savings by applying efficiency from downstream to upstream, as I'll explain shortly. We reward the design professionals for what they save, not for what they spend. And we optimize the sequence and the timing of design steps. So to keep people comfortable in hot places, first, we cool the people, not the building, which has no comfort sensation. I once asked my hostess in Tokyo why she didn't heat her house, and she very sensibly replied, "Why should I? Is the house cold?" So these hyper chairs at RMI's Basalt office use 3.6 watts of silent fans to keep you comfortable up to about 30 degrees. Then expand the range of conditions in which people feel comfortable, for example, by 5 to 7 degrees with good ceiling fans. Then minimize unwanted heat and humidity gains within or into the space. Next, apply passive cooling. Next, active but non-refrigerative cooling. Next, tripled efficiency refrigerative cooling. Next would come cool storage and controls. But actually, we need never go as far down the list as refrigerative cooling to save about 90 to 100% of cooling energy with better comfort and uptime and lower whole system capital cost, even in the most severe climates. Yet most practitioners pursue these options in reverse order, worst buys first. Integrative design let our Empire State Building retrofit save 38%, later 43% of its energy with a 3-year payback. 3 years later, our cost-effective retrofit saved 70%, making this half-century-old government complex more efficient than the then best new US office or the best Japanese small office retrofit, Takanaka's Higashikanto office, done without interrupting its occupancy. But both those buildings use 3 times more energy than Rocky Mountain Institute's net positive, no mechanicals, passive office, 10 minutes from here in the coldest North American climate zone. Now, this German building is reportedly using 2/5 less energy than ours. Yet all these technologies existed more than a decade ago. What mainly improved is not so much technology as design, and it keeps improving. The Empire State Building's owner now wants to double its savings to 80%. That Empire State Building retrofit remanufactured all 6,514 windows on site into super windows that pass light but block heat, plus better lights, office equipment, etc., cutting the maximum cooling load by 1/3. Then renovating smaller chillers instead of adding bigger chillers saved $17 million of capital cost, paying for most of the other improvements and cutting the payback to 3 years, or less than 1 year if we had counted non-energy benefits to the owner or the tenants. A major energy service company had also offered a 3-year payback, but with disintegrated design yielding only 1/6 the savings we got. Similarly, in 6 muggy Indian cities, 1.5 million square meters of integratively designed offices use 80% less energy than the Indian norm, with 10 or 20% lower construction cost, yet superior comfort and satisfaction. Glare-free daylighting is delivered throughout by contract. If workers complain of glare and demand blinds, the architect doesn't get paid. And yes, that building was flipped upside down, saving more mechanical cost by shading than it added structural cost. IPCC 7 years ago assessed diverse European new buildings on the left and retrofits on the right, with bigger savings toward the right in both graphs. The best buildings saved up to at least 90% of their energy without costing more per unit of saved energy. The vertical cost scatter shows the business opportunity to conform inferior projects to the low-cost projects' best practices. The latest international comparison ranked Japan's commercial buildings 16th in efficiency among 25 countries. Its houses 6th, so there's much Kaizen to do. Timing matters too. When retrofitting a big glass office tower, super windows plus efficient lights and equipment can shrink mechanical loads and systems by 4-fold, more than paying upfront for the efficiencies that shrank them. A 4-fold efficiency gain in this old Chicago building could thus pay back in about -5 months, cheaper than the routine 20-year renovation that saves nothing, if you coordinate that deep retrofit with the routine renewal of the curtain wall facade. Deep retrofits of all our big buildings will take decades, so let's right time them to make the savings much bigger and cheaper. The best big building air conditioning systems in Singapore are already 3 times as efficient as the norm there or in Japan, yet they deliver better comfort and cost less to build. But in a recent experiment, a shaded pavilion the size of a bus stop shelter kept Singaporeans comfortable outdoors without fans or breezes and without drying or cooling the hot, humid air. People were instead cooled purely radiatively by absorbing far infrared radiation from their bodies into vertical panels circulating 17-degree water, separated from humid air by a plastic sheet to prevent condensation. Panels cooled to 23 to 25 degrees can thus deliver comfort in outdoor temperatures up to at least 32 with 80% relative humidity. That modest cooling can even be achieved by special surfaces that passively radiate infrared rays to the sky in any weather. So even in direct sun, they feel cool to the touch. Combining these passive technologies may provide summer comfort in buildings and vehicles in the Kansai climate using no or almost no electricity. Perhaps it could even be retrofitted into old masonry buildings. Japan has some wonderfully efficient appliances, but technology keeps advancing. In Switzerland, this fist-sized heat pump can deliver 6 to 15 units of hot water per unit of electricity. This dramatically more efficient, safe, and otherwise superior electric cooking system uses vacuum-insulated pots, also with a teppanyaki option. Both these systems are several-fold more efficient than the best in Japan. Across diverse sectors, our $50-odd billion worth of industrial retrofit designs typically found about 30 to 60% energy savings, paying back in a few years. And in new builds, about 40 to 90+% savings with generally lower capital cost. That's much better than the brown retrofit zone most energy service companies deliver, shown here in the upper left corner. And our better systems come from rethinking industrial processes and redesigning basic elements like pump, fan, and motor systems. For example, in both buildings and industry, better pipe and duct design can save about 80 or 90% of friction, 97% here in my house. If everyone did it, this could save roughly 2/5 of the world's electricity, or half the coal-fired electricity, typically paying back in less than a year in industrial retrofits and instantly in new builds. We need simply design big pipes and small pumps, not small pipes and big pumps, and lay out the pipes first, then the equipment. So in this example, on the left, the low friction pipes make the blue pump so tiny that it looks like a decimal point error. And it's raised up to meet the pipe rather than conventionally dipping the pipe down to meet a pump on the floor. On the right, these 10 chillers, normally in a neat row, are staggered to eliminate the pipe elbows and their friction. Yet such rearrangement of designers' mental furniture remains largely unnoticed and unpracticed because it's not a technology. It's a design method, and few people yet think of design as a scaling vector, a way to make things big fast. In California's Oakland Museum, our treasured colleague Peter Rumsey retrofitted an efficient piping layout that cut the pumping energy by 3/4 with a 2 or 3 month payback and eliminated 15 pumps that will never again waste energy and maintenance costs. Repiping another pumping loop and adding variable frequency drives doubled the flow and saved 85% of the energy. Peter simply asked the pipe fitters to lay out the supply pipes as if they were drains. Here's how most big buildings pipe cooling tower water back to the condenser. If we lay it out instead, as Peter does, everything gets better. The only obstacle is force of habit. We should bend minds, not pipes. What does such savings mean for the pumps and fans that use half the torque of the motors that use over half the world's electricity? From the fuel burned in the power plant to the end use, many successive losses compound. So only 1/10 of the energy in the fuel comes out the pipe as flow. But now turn those compounding losses around backwards into compounding savings from right to left, and every unit of flow or friction you save in the pipe saves 10 units of fuel cost, emissions, and global weirding at the power plant. And as you go back upstream, the components get smaller and cheaper, reducing the total capital cost. So always start your savings downstream, start at the end with intent, with purpose. Then your design logic flows back upstream in the opposite direction to the energy flow. This works even in modern high-tech industries. We've shown how to save at least 95% of the energy in data centers and half their capital costs. And in chip fabs, how to save 2/3 of the energy before improving the chip making tools and half the capital cost and all the chillers. Tenfold energy savings in, say, pumping may seem incredible to you, but at this moment, your heart is pumping blood about 10 times as efficiently as typical industrial pumping systems do. If your roughly 100,000 kilometers of fractal blood vessels had the design and friction of standard industrial piping, you would need a heart bigger than your body. Very inconvenient. But in fact, your 1/3 of a kilogram, 1.5 watt heart suffices because your blood follows nature's standard design, laminar vortex flow. That's a whole other conversation about the other main design revolution, biomimicry, or innovation inspired by nature, like the Shinkansen's train's nose inspired by the beak of a kingfisher bird. Even in Japan, with the world's second most efficient industrial sector, there's always more Kaizen to do, and not only in the factories. Industry makes and applies materials, but elegantly frugal design can save at least half the world's cement and steel that now release about 15% of the total CO2. Substituting tension for compression structures typically gives better strength, aesthetics, and cost with 1/8 the tons. Fabric forms permit optimal shapes that can save over half the concrete in beams, sheets, and other common shapes to deliver the same or better strength and stiffness. And then the weight savings multiply or snowball or compound because you need less strength to hold up less weight. This folded concrete roof, pre-stressed with carbon fiber, is just 4 centimeters thick, but it replaces a 30 centimeter thick steel and concrete slab. It costs less, and it saves 3/4 of the materials. This rendering of an airy bridge in Holland shows how 3D printing can eliminate most of the weight of concrete structures that mostly support their own weight. This beautiful stainless steel bridge was 3D printed. Next, substitute natural composites like wood, already in 85-meter towers and planned for 350 meters in Tokyo. Add carbon fiber to save much of the wood or concrete. Apply Taiheo's carbon-neutral bamboo concrete, and perhaps adopt carboxylate chemistries to make cement a net absorber of CO2. Finally, the same design logic also works for vehicles, where Japan in 2018 ranked 16th in automotive and 19th in freight efficiency of 25 countries. Automobile's propulsion system, or powertrain, loses 4/5 of the fuel energy before it ever reaches the wheels. But our savings should start at the wheels. Here's why. Just 1/5 of a modern car's fuel energy reaches the wheels and moves the car. Of that so-called tractive load, nearly half heats the air that the car pushes aside. Most of the rest heats the tires and the road. So only the last 6% of the fuel energy accelerates the car and then heats the brakes when you stop. But 19/20ths of the mass you're accelerating is the heavy steel car. So just 1/20th of that 6%, or about 0.3% of the fuel energy, ultimately moves the driver. Not very gratifying after 1 1/3 centuries of devoted engineering effort. Moreover, both acceleration and rolling resistance depend on mass, which thus drives most of the tractive load, causes most of the tractive load. So reducing losses in the powertrain is harder than reducing tractive load. It's also less rewarding because saving 1 unit of energy in the powertrain saves only 1 unit of fuel in the tank. But saving 1 unit of energy at the wheels avoids 4 or 5 more units lost getting that energy to the wheels, leveraging 5 or 6 total units of energy saved at the tank. Thus, we should first reduce tractive load, then improve the powertrain, which then shrinks for the same acceleration, saving more weight, and also saving capital costs to help pay for the lightweighting. That's how BMW proved lightweighting can be profitable even at the carbon fiber prices of 2013 with this carbon fiber electric car, the i3 that I've driven for 5 years. It made money from the first unit off the assembly line. Sandy Munro, the normally understated doyen of automotive costing, called it the most significant vehicle since Ford's Model T and the most advanced vehicle on the planet. Validating our 1990s claims, its carbon fiber is paid for by the batteries that its lightness saves, and fewer batteries mean faster recharging. Its integrative design decompounds mass far more than usually assumed. Its manufacturing is radically frugal, confirms the elimination of the conventional body and paint shops, the two hardest and costliest steps in making a car, and it's much better for workers. And it quadruples efficiency, 53 kilometers per liter equivalent, without compromise and with many driver advantages. My Society of Automotive Engineers paper last year showed with 15 empirical examples like this from the global auto industry's products and designs that such whole vehicle design can save several-fold more energy than normally assumed, yet at lower cost. But now we can go even further. That's most drivers will never need to recharge this two-seat electric car because its solar cells capture enough energy to drive about 20 to 60 kilometers per day, depending on your climate zone in Japan. It's as if your present car magically added about 7 liters of fuel to its tank for every day you park it outside. To make a long trip, you can very quickly recharge the batteries with household electricity for ranges up to 1,600 kilometers. My BMW and Tesla electric cars here are among the most efficient sold, but this two-seat carbon fiber model will nearly triple their efficiency to more than 146 kilometers per liter. The carbon fiber body looks very crashworthy. And based on Toyota's wonderful triple efficiency 4-seat 1X carbon fiber concept car 14 years ago, perhaps Japanese automakers could make vehicles like this one even lighter. And the Dutch firm Lightyear plans to offer a 5-seat, 725 kilometer range, lightweight aerodynamic 4-wheel car whose 5 square meters of solar cells and high efficiency can add 12 kilometers of range for each 1 hour in the sun. Better design and technology keep expanding opportunities even in heavy vehicles. We've known for over a decade how to make trucks 3 or 4 times more efficient and airplanes 3 to 5 times more efficient before electrification. Now Tesla's semi-electric truck, 40% sleeker, and partly light-weighted to offset its batteries, roughly triples efficiency with a 2-year payback at low US fuel prices. Then among over 100 aviation startup companies, this long-range air taxi revealed last August could fly nonstop from Tokyo to Sydney with 1/6 a business jet's operating cost and 1/8 its fuel use, even before electrification. That looks set to blow up everyone's current business models. We could even make vehicle structures like airframes 2 orders of magnitude, roughly 100-fold lighter still. MIT Center for Bits and Atoms and NASA tested last year a 4.3-meter test structure 59 times less dense than a typical aircraft wing, with the strength and toughness of bulk elastomers, but the gossamer density of aerogel. Eliminating movable flight surfaces, its whole shape adapts passively and continuously to real-time flight conditions like a bird's wing. Thousands of such identical molded polymer cells can be assembled by swarms of programmed robots into an airplane of any shape and size, opening revolutionary prospects for lightweighting, aerodynamics, and cost reduction. It's been prototyped as a car for Toyota and an airplane for Airbus. It can make a vacuum balloon, needing no helium, light enough when evacuated to be buoyant in the atmosphere without crushing, and lift 24 times the payload of a jumbo jet. These lattice structures are made of common engineering plastics, but could perform an order of magnitude better with carbon fiber, 2 orders of magnitude better with carbon nanotubes. So to summarize, Japan has many gifted designers who cultivate beginner's mind, giving integrative and biomimetic design immense potential. In the coming decades, we can see profitable paths to probably quintupling global energy efficiency, then saving even more. That would make Tony's future much easier. Yet this design revolution in efficiency is seldom recognized or taught or delivered or expected or rewarded. Observing buildings, vehicles, factories in over 70 countries in 50 years, I see the same design errors repeated everywhere because they're widespread in our textbooks and in our classrooms. So I'm hatching a plot for, to put it impolitely, the nonviolent overthrow of bad engineering. Teaching disintegrated design condemns our descendants to perpetual retrofit of inefficient systems, not a worthy legacy. To help us be good ancestors, I'm seeking fellow students and teachers and practitioners, especially in Japan, to collaborate on making integrative design shift rapidly from rare to common. I hope these little examples will encourage you to rethink why end-use efficiency is only a small fraction of what it could be, how better design and beginner's mind can help close that gap, and how we can scale up to make integrative design grow quickly everywhere like bamboo. Then, as we strive for zero muda, the global energy transformation can move at the pace and cost of design and of software, not of infrastructure, and can be not constrained by the inertia of incumbents, but sped by the ambition of insurgents, like many of you. So thank you all for your good work and your kind attention. ご清聴誠にありがとうございます。
Thank you, Amory, for this very thought-provoking, constructive presentation on the role of integrative design and new material opportunities for lightweight, energy-efficient structures. But one problem when listening to what you describe is trying to understand why these insights are not used. We had an exchange, I think, a year ago with an engineer who wrote about this thick pipe, small pump solutions already in the 19th century. And still this is not used. Can you try to explain why?
I think because people are creatures of habit. Do you know why the railway gauge of American railways is 4 feet 8.5 inches? Sorry about the unit, but it's a certain distance apart. It's because the British railways were that size, because the trams were that size, because the wheelwrights or the wagon wrights didn't want to change their jigs and tools when they switched from wagons to trams. So why were the wagons using that space between the wheels? Well, because they had to fit the ruts in the roads or they would shake apart. Who made the ruts? The same people who made the roads, the Romans, 2,000 years earlier. So the next time you look at some traditional way we design things, and you say, what horse's ass designed that? You may be exactly right, because this dimension is determined by the size of the back ends of 2 Imperial Roman army war horses. Oh, it gets better. We have to ship our space rocket boosters from Utah through a railway tunnel to get to Florida and launch them. The size of that tunnel is also determined indirectly by the size of the back ends of 2 Imperial Roman army war horses. And that determines how long our boosters can burn and how much they can lift into space today.
Yeah, thank you. Tony, you heard now Amory talking about integrative design and the opportunities in material science to improve energy efficiency, reduce weights, and make everything you described easier. How do you see the connection between Amory's opportunity map and the disruptive transitions that you are predicting?
Yeah, I think that at the end of the day, the question that we need to ask is, what are we maximizing? What are we optimizing, right? And in the past, we've worked in silos. So people have optimized things in their little silos, and they've optimized things for their little silos. But now that, I love Amory's, systems thinking and design thinking, and that is the crux of the matter, right? We need to design essentially the world as a system. It's not either or. It's not, the transportation thing here and the energy thing there and the food thing there. We need to design pretty much everything at this point. I've said for a while that because of these technology disruptions, the 2020s are going to be the most disruptive decade that we've ever seen. So that gives us an opportunity to essentially create, we're between two ages, if you will, the new age, right? Where, transportation and energy and food, and we design everything for humans, right? Integrated. And I agree that, our biggest challenge is imagination. It's not raw materials, it's not technology. We have everything we need to make this happen, but we're fighting the baggage of incumbency. And that baggage in some ways is, could be 100 years old, and in other ways that comes from the Romans, right? As Amory mentioned. But now we have a big opportunity to essentially use systems thinking to put together all of these things and, essentially bring on what I call the age of freedom, right, for everybody. So that is the biggest challenge.
And in principle, Japan could do this any better than anyone because you have such wonderful system thinkers designing all these amazingly integrated devices. We just need to apply that thinking more widely than a single device. And I think Tony got the economics of the renewables exactly right. They and efficiency are both very cheap. They're both getting cheaper, but we're in a climate emergency. We're in other emergencies, including a resilience emergency. And we and many other people all over the world need to do all of these things as fast as possible to head off, to avoid the worst consequences of silly things we did before.
One of the challenges in Tony's solar wind battery 100% solution is the management of electric power. And Tony described it as one where you do the superpower. You build more power generating capacity than the current need is, and you balance with storage. When you talk about energy efficiency, how would that affect the power balancing challenge for renewable systems, Amory?
It would make it very much easier, and you would need a lot less investment on the supply side, but also you'd be more resilient if things went wrong, because the system would be more fractal. Let me take this example. My house here has had one power failure in 25 years. That's when a battery cell failed. Some of my neighbors had 8 power failures in one morning. If you were in Texas right now experiencing extreme cold, or in other events in Texas or Japan experiencing extreme heat, if your house is efficient, you will be safe. And by the way, if it's cold, your pipes won't freeze. If your solar power on your roof is wired as it can safely be under an international standard to work with or without the grid, then if this amazing miracle of the grid powered in Tony's way were to fail, your house would still be okay because the system is fractal. It can decompose into small pieces, into microgrids or nanogrids. Each will work as long as necessary. And when the grid comes back, if it does, everything will resynchronize and reconnect. But meanwhile, you're safe. And I think we need to design our society in that way. So yes, there is a lot of wonderful control we can do, and we can distribute the intelligence in the grid so all the moving parts talk to each other rather than having one dispatcher telling all the electrons where to go. I think we're moving in that direction. It'll be more like the energy flows in a natural ecosystem. But resilience first, and efficiency gives you the most bounce per buck, the most resilience in using the supply you have.
And Tony, in your scenarios for the 3 states in the US and elsewhere, to what extent was that decentralized storage, and to what extent was it centralized, and how was the infrastructure cost compared to the model that Amory just described?
Yeah, so that one study was, essentially grid agnostic. What we wanted to know was if it was possible, right? And if so, at what cost? We did not want to be bound when we did that study to the existing grid, in other words, right? We wanted to study if it's possible, and then secondarily, what is the right design for the economic system, right? The transportation system and so on and so forth, right? Based on that. But, based on all our work, my previous work and that of Amory's and others, basically what's coming, what we're building is a network-based design where we have distributed generation and storage, where every single node can essentially survive and thrive even independently of every other node. So think of it as an internet of energy, if you will, or internet of transportation, if you will, where everything is connected and independent, right? And so that's where we're going. Again, one of the things that I didn't mention is the idea that, we've talked about grid parity, but I think that the key is what I call God parity. GOD is generation on demand, meaning that the cost of rooftop generation is cheaper than the cost of transmission. So, at that point, even if utility scale is 0, it's still cheaper to generate and store locally your house, your business, and so on and so forth. Furthermore,
it's true in Japan. Since 2014, I think that solar power on your roof is cheaper than grid power. And now the same is true also with batteries.
Yeah, and it's getting even cheaper, right? And in different geographies have different costs, right? Of transmission and so on and so forth. But it's getting to be that way in hundreds of markets. And then if
at the point in both countries where, if say the nuclear part, which is about 1/5 of the capital cost of a nuclear power plant, were free, the other roughly 4/5 or 3/4 of the capital cost would still be several-fold more expensive than modern renewables. So there's no kind of nuclear technology, steam cycle technology, that can ever compete on the grid now.
It can't. And I'm going to publish something over the next few days that shows actually that the levelized cost of electricity that the industry publishes actually has been wrong for 10 years. They've been underestimating the actual cost of a new power plant, and if for 10 years, and if we take that and actually we extrapolate over the next 10 years, the cost of a new nuclear plant in 2030 should be about 100 cents per kilowatt hour, 100, and the cost of solar is like 1 cent already, right? So 100 times more expensive than solar.
And let us bear in mind that cost has climate consequences, because as I think we'd all agree, many of the world's nuclear plants and essentially all the fossil fuel plants cost more to operate than they can earn, let alone paying for their construction cost originally. Well, that means if you close such a plant that's uneconomic to run, and you use the saved operating cost to buy instead efficiency or cheap renewables, whatever's cheapest, you will save more carbon per yen. It will be more climate effective. So the notion that because we have, for example, nuclear plants, we should run them, we should restart and run them just because they're there already and they'll save carbon in fossil fuel plants is actually not correct, because if it's cheaper to do the same job with efficiency or renewables, we'll save more carbon.
I want to touch on what, I'm sorry, Tomas, on what you said, Amory, about, the network design, because it's far more robust, right? And resilient, which means, it's more difficult to push down and faster to come back, right? Centralized systems are more fragile, right? And we saw that in Texas, for instance, and we've seen that in Japan and in many other markets. Centralization is fragile. And the more we can distribute, right, to energy generation and storage to the nodes, to everybody, in other words, we'll have a more robust and resilient infrastructure. And one of the things that is not priced into the existing power plants is that cost of fragility, right? I mean, did anyone care to put all the costs of an economy when a nuclear power plant goes down? Not just the direct cost, but the cost of fragility, or in Texas, right? Amory?
And this is the Japanese translation of still one of the books on the subject, which I wrote for the U.S. Department of Defense in 1980-81. Exactly your point.
And you're so far ahead of our time, Amory. That's great. Yeah.
You too.
Thank you. I think we are well beyond the scheduled end of this session. And I think it was certainly inspiring, intelligent start of this conference. I think you have shown very clearly that the worst problem is getting rid of all old conventions and old thinking, and see the opportunities that technology provides for a more robust, resilient, socially favorable solution to the global energy problems. And as Amory has shown, thinking ahead is good, and your reputation will be strengthened over time. And I think Tony's predictions will, of course, be tested. And I belong to the optimists regarding this development. I think you will be proven right, just as Amory has been in many of the predictions he has made. We are now going to have a break in this conference and meet again at 2:00 Japanese time. And I think this will be a very encouraging and interesting part of the conference as well, because we will hear some descriptions of the more concrete implementations of the technologies and solutions that you have now described and predicted. So again, thank you very much. I don't think I've ever got up at 2:00 in the morning and felt that it was so worthwhile than listening to your presentations and this discussion. And I hope to see you all again in some time at 2:00 Japanese time when we resume the session. Thank you.
Thank you. Thank you. Thanks.